Morning, everybody, or again, I guess, whatever time. We're starting our gas unit today, so um, this unit is going to be a lot of review. Also, there's not a lot new here. Um, in fact, really until the end of the semester, there's a couple new things in the next unit when we talk about solutions, but there's not a lot of new stuff up through the end of the semester. So, the gas unit is going to be a good unit to start practicing not using your calculator on the multiple choice questions. All right, so I'm going to give you an AP packet this time, and we'll talk about how that works. But basically, it would be a very good idea this time through while you're working on your AP questions to not use your calculator on the multiple choice questions in specific. So we're going to practice some mental math techniques and stuff like that. I don't know how much of that I'm going to get done on the video because most of these are sample problems from the book where they're assuming that you are using a calculator. So we'll probably talk more about that in class, but I just wanted to mention it just to remind you that this is the unit where we're going to start doing that. This is a picture of the sun, really kind of a picture of what any star is going to look like. On the surface, you've got a lot of helium and hydrogen gas there, okay? And obviously it's very, 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 very hot because there's fusion reactions happening in the sun. So that's how that's applicable to the gases unit. You know all of this. Gases are a little bit different than liquids and solids, and actually we're sort of doing this backwards from what you might think. We're going to talk about gases first, and then we're going to hit liquids and solids in the next unit. So they have no definite volume or shape. All right, they will spread out to fill a container, and they will take the shape of whatever container they're in. Okay, they expand to fill their containers. That kind of goes with having no definite volume. They're highly compressible as well because they're so spread out. Because those gas particles are so far away from each other, it's easy to compress them to push them into a smaller space. They have extremely low densities. All of these are very much related. Because gases tend to spread out, there's a lot of space between the molecules, and that means that they're not very dense. And they will mix completely with any other gas. So you put, helium gas and oxygen gas together. The two, because of the random motion of the particles, because gas particles are moving so quickly, and because they're so spread out, you give them a little bit of time and they will completely be mixed together in a homogeneous mixture. Oh, and they exert pressure on their surroundings because the gas particles, again, are moving so quickly, basically independent of one another. They're going to push against any container that they are in, hit the side walls of that container, and they're going to exert pressure on it. So those are the characteristics of gases. This is not in your notes. Your notes are a little bit different than the PowerPoint, so I'll try and alert you when that happens. But just in case you're interested, the Earth's atmosphere is primarily, and I think we talked about this last year, primarily nitrogen and oxygen. 78% nitrogen, about 21% oxygen. And then the rest of it is made up of several different gases. You've got quite a bit of argon in there relative to some other gases. Carbon dioxide is a surprisingly small amount of the Earth's atmosphere, and then you have methane, hydrogen, and then there's some other trace gases there as well, but those are the main ones. Okay, so let's talk about pressure a little bit. Okay, this is a concept you're going to be very familiar with if you have taken physics at this point. Pressure is just force divided by area. So, I don't remember if we talked about this last year or not. I don't think we did. But if you have ever seen on television or maybe actually in person someone laying on a bed of nails, that has to do with this idea of pressure. Okay, so if someone lays across an entire big bed of nails, then they can actually do that without breaking their skin if they're careful, if they know what they're doing. But if someone tries to lay on one nail, all of their body weight on that one little point, that's going to put way too much pressure on their skin, and it's going to break right through your skin. Okay, so you distribute your weight over many different points, and there's less pressure on any given point, and that's why your skin is tough enough to keep from breaking when you spread out that force a little bit. But if it's all in one tiny little area, then that's a very high amount of pressure, and that's going to poke right through your skin. So that's why it has to be a bed of nails and not just one nail. So if you're looking here at the surface, wherever you are, there is a lot of air on top of you. Okay, we have quite a bit of atmosphere on Earth, and so all of this air right here, air doesn't seem like it would have that much weight, but it does add up. Okay, so you've got this meter squared column of air here, and the mass of that is actually 10 to the 4th kilograms, and all of that is pushing down on this 1 square meter. Okay, so that's air pressure. Okay, that's what creates the pressure that we feel, this 1 atmosphere of pressure at the surface, and this is actually a high amount of pressure. I think I did some gas demos for you guys last year. Sometimes I have trouble remembering what I did for AP and what I did for honors. But some gas demos where we crushed a can just by essentially creating a vacuum inside the aluminum can, and the atmospheric pressure outside of it just crushes the can. So that's an example of how strong air pressure actually can be. So it's the weight of air per unit of area, and weight, we're talking about force, because force is really mass times acceleration. We talked about that in an earlier unit, okay? And the acceleration due to gravity is 9.8 meters per second squared. So then you just take the mass of that air, multiply it times the acceleration, that'll give you the weight of the air. So then you just plug that in here. The weight of the air divided by the area that air is in, and that's going to give you the air pressure. Okay. Obviously, the higher up you go, the lower the air pressure, because the less air there is pushing down on you. So at Mount Everest, you got an elevation of about close to 9,000 meters, and the air pressure is greatly reduced there. It's less than 0.4 of an atmosphere. But you have to get up pretty high before that starts to happen. Even at a mile high, if you notice here in Denver, the pressure is still going to be 0.85 atmospheres. But if you've ever seen on the cooking directions on, and I think we talked about this last year too, but the cooking directions on a pasta box has different cooking directions for high elevations. So if you are, this is kind of extreme, but if you are making pasta on Mount Everest, the water is going to boil a lot faster because it has less air pushing down on it. If you've got a beaker of water here, okay, and you're boiling this water and it starts to escape as a gas, really the reason that water takes so long to escape as a gas has to do with the intermolecular forces, but it also has to do with the fact that there's air pressure pushing down on these particles, keeping them from leaving. Okay, the less pressure pushing down on them, the easier it is for them to leave. And so, water on Mount Everest might boil at, I really don't know exactly, but maybe 60 degrees Celsius instead of 100. Okay, if you can only get your water up to 60 degrees, you're going to have to cook your pasta a lot longer in order to get it to cook. And so that's why for high altitudes they have different cooking directions, and they usually tell you to cook it a little bit longer. Okay, this I don't think is on your notes, but the rest of this should be. The SI unit for pressure is going to be the Newton meter. Newtons divided by meters, or Newton meters squared, I guess. Newtons divided by meters squared, which is the same thing as 1 Pascal. Okay. And we talked about all these units of pressure last year as well. 1 atmosphere is 101,325 pascals, or 101.325 kilopascals. You might write that in, because I don't think I have that up here. I probably should. 101.325 kPa. Now, you don't need to memorize any of these atmospheric conversions. They are all on your equation sheet that I've given you. Okay. And so all the ones that you would need, they don't expect you to memorize those. They have those provided for you. And then one that we didn't talk about last year, I don't think, 100,000 pascals is equal to 1 bar. And sometimes that's used as a measure of atmospheric pressure. So here's all the different conversions that you might need here. 1 atmosphere equals 760 millimeters of mercury equals 760 torr. These two units are basically the same thing. Equals 1013.25 hectopascals. It's kind of a strange unit, but sometimes that is used. So it's 101.325 kilopascals. It's 1013.25 hectopascals, because I don't know if you remember that prefix hecto, but it means 100. Kilo means 1,000. So, and then here's the psi, 14.695 psi. And then sometimes meteorologists will use the millibar. 1 millibar is 0.001 bars, which is 0.1 kilopascals or 1 hectopascal. And that's why sometimes we use that unit, because it's equal to a millibar. Okay, so lots of conversions there. Whoops, that's not what I meant to do. So here's, you might have a pressure conversion problem. I doubt that you would have one where you just have to convert the pressure, but you might have one where that's built into the problem a little bit. So let's practice one of these. Barometric pressure reported for Butte was 1,018 hectopascals. So now we want to know, what is that in torr, atmospheres, and bar? This is just dimensional analysis, so you shouldn't have any problem at all with this. 1018 hectopascals. We're going to go from HPA to torr. And to atmospheres. And to a bar. And again, really there's nothing for you to memorize here. It's all, you're going to use all of these equations, conversions that they give you on the AP exam. So 1 hectopascal is, well, okay, I guess it's not a 1-to-1 ratio here, the way that it's given. 760 torr and 1013.25 hectopascals. Forgot that number already. 1013.25. Okay, and then 1 atmosphere. Okay, so that one, 1013.25. And then in a bar, 0.001 bars equals 1 hectopascal. Okay, so we're just doing all these conversions here. Pretty easy stuff. So it should be right at 1. One torr. How many sig figs here? Actually, I guess I should go 1.005 torr to get my 4 sig figs in. The next one, 1018 divided by 1013.25. Wait a second. Didn't do that right on this one, sorry. 1018 times 760. Forgot to do that part. 763.6. 0.6 torr. And then, so this one's going to be 1.005 atmospheres. Yeah, that seems more right. 1018 times 0.001, 1.018. And yes, I did do that on my calculator, and yes, I am a hypocrite for having done that right after giving you a speech about not using your calculators anymore. So, okay, units of pressure. A couple of units that I want to focus on a little more specifically, the millimeters of mercury or the torr, and really they're kind of the same thing, so really one unit. When we measure pressure using millimeters of mercury or torr, basically what we have here is a mercury bath with a tube inside it, okay, and there's a vacuum. All the air has been sucked out of this tube right here. And so then what happens is the air pressure pushes down on the mercury bath and pushes the liquid up into the column here that has a vacuum in it. So there's no air pressure up here, right? So depending on how high it pushes the column of mercury, that's a measure of the pressure. So really, millimeters of mercury, I mean, all that is we're just measuring this height right here in millimeters, okay? And the reason I'm bringing that up is because this might not be on your notes either. I probably should have just taken this slide out. Yep. Because I think, I guess the one thing that's on here, the 14.7 pounds per square inch, it looks different than the number that we had over. Let me back up a second here. No, 14.695. Okay, so 14.7. Yeah, I would go with 14.7. But the reason that I wanted to talk about this is because of the manometers or manometers. I'm really not sure how to pronounce those. But we did some of these types of problems last year, manometer problems. And what this is you've got this special sort of device where you've got a gas inside of a bulb here, and then you've got a curved tube, okay, and you've got the atmospheric pressure pushing down on one side, and you've got the gas pressure that's inside the tube pushing the other direction. So there's kind of a fight here between the gas in this bulb and the atmosphere, the gases in the atmosphere, okay? And you can actually measure the pressure of the gas that's inside this bulb based on the difference in the heights of the columns, okay? So, and here's the formula right here. The pressure of the gas is equal to the pressure of the atmosphere plus the pH, which is just the difference in height. And usually we're going to do this in millimeters of mercury. They might give you different height units like inches of mercury or that sort of thing, but usually it's going to be in millimeters of mercury. Okay? All right, so we've got a sample problem here, and this is kind of a long one. Barometer showing atmospheric pressure to be 764.7 torr, which again is the same thing as millimeters of mercury. Sample of gas placed in a vessel attached to an open-end mercury manometer or manometer. And then they're using a meter stick to measure the height of the mercury above the bottom. And they're telling you the heights on both of the arms here. Okay? And they want to know the pressure of the gas in atmospheres and in kilopascals. Okay, I don't know if you remember this from last year, but the thing that I always told my students was draw a picture of these. Okay, it's much easier if you draw a picture. So basically what you're going to have here, you're going to have your gas. It's been a while since I've made a picture of these. I was okay at this last year. I'm probably not going to be now. So it's going to go down, and then it's going to curve back up like this. Okay, and then you've got something that looks like that. Okay, that is not a very good drawing. But draw yourself a picture, because that's going to help you. Okay, so you've got your gas inside your tube here, and then we need to read basically what's going on here. So 764.7 torr is the pressure in the atmosphere. That is the pressure pushing down on this tube right here, 764.7. And I'm going to label this millimeters of mercury because that's the same thing as torr, and these heights are given to us in millimeters. So that's going to make all our units look the same here. Okay, so the level of mercury in the open end arm, that's this part right here. Okay, that's the open end arm because it's open on the end. And it has a measured height of 136.4 millimeters. Okay, so right here, 136.4 millimeters. That in the arm that is in contact with the gas has a height of 103.8, so that's going to be a little bit lower, okay? And that's just measuring from the bottom down here, okay? So this one's 103.8. Again, this picture is just not awesome. So basically, we've got a difference in height between these two, and we have to figure out what is the difference in height. Okay, so 136.4, 103.8. This would be a great one to do in your head, just for practice. That's going to be a difference of 32.6 millimeters of mercury. Sorry, this is just messy. So we have to think about what that's telling us, okay? And remember, last year I really said just think about these, okay? That's the best way to do these problems, is just to think about them. And what's happening here is this gas, whatever gas this is, it is winning the battle, essentially, because this gas is pushing down on the mercury here. Okay, this is the mercury. Okay, this gas is pushing down on the mercury, and so is the atmosphere, but the atmosphere is losing because this gas is pushing the mercury down further than the atmosphere is, okay? And so what that means is we've got this 764.7 millimeters of mercury here. That's the pressure pushing down from the atmosphere. The gas must actually have more pressure than that, okay? And so what that means is this difference right here, this 32.6 millimeters, we need to add that to the atmospheric pressure. Okay? And that's going to give us the pressure of the gas. And again, don't think about do I add or do I subtract when the levels are different. Just think about which one is winning, okay? This gas inside here is the winner here, and so it must have a higher pressure than atmospheric pressure. And the only way to get that is to add the difference between the two, okay? So 764.7 plus 32.6, it's going to give me 797.3 millimeters of mercury, okay? Unfortunately for us, they are not asking for this pressure in millimeters of mercury. They're asking for this pressure in atmospheres and in kilopascals, all right? So for A here, we just need to do a quick conversion, 797.3 millimeters of mercury. Convert that into atmospheres, and I believe it's 760 millimeters of mercury in 1 atmosphere. So 797.3 divided by 760, we do not sig figs here. We need 4 sig figs in this one, it looks like, so 1.049 atmospheres. Okay, so that's the answer for A, 1.049. Now the other one here, in kilopascals, I'm going to have to erase this because I ran out of room here. So for B, 797.3 millimeters of mercury. Just do our other conversion here. Let's see here. This is 760 and 101.325, I think, if I'm remembering that right. So then the 797.3 times 101.325 divided by 760 gives me 106.3 kPa. Okay, which again, if you think about this number, that sort of makes sense. There's 101.325 kilopascals in an atmosphere. This is a little bit higher than atmospheric pressure to begin with, because 760 millimeters of mercury is 1 atmosphere of pressure. So we would expect our kilopascals to be a little bit higher than 1 atmosphere of pressure, because the pressure of the gas is even higher than the pressure of the atmosphere. Okay. All right, so that's the manometer problems. I might give you a little bit more practice on those in class. You're probably not going to see, I've seen a couple of those on AP exams. It doesn't come up that often, so I'm not going to spend a lot of time on that, but it would be something good to practice just to make sure we understand how to do that when we're talking about the difference in the heights of the mercury and how that relates to the pressure. So I think that's it for this set of units, or set of notes. So we will just continue talking about the gas laws next time.